Hey everyone and welcome back to PrepFusion. I'm Anish and today we'll start the lecture 1 of rectifiers. So in the previous lecture we learned what rectifiers are, we learned the parameters of rectifiers, then we analyzed for a half wave rectifier with a pure resistive load with controlled and uncontrolled. For uncontrolled we just need to make the triggering angle 0, and for control we will trigger the SCR between 0 to pi. Okay, we learned about the parameters, so you need to, if you are not able to grasp all these things, sometimes you need to revise as well, and sometimes just what are the main things that you need to keep in mind. The results that I derive at the end, how I derive those, what were the parameters. One thing was my my half wave rectifier, right, can only conduct from alpha to pi. It cannot conduct after that or before that. So I am only integrating that alpha to pi. How did that derivation came? Why was alpha there at the lower limit? Why was pi there at the upper limit? All those things you need to keep in mind. Don't need to remember the formula that it was equals to Vm by 2 pi into 1 plus cos alpha, the average voltage. Even if you don't remember the formula, but how did I derive that? That is more important. Derivations are more important here because there will be so many formulas you won't be able to understand. And someday GATE will give some question which is unconventional and no formula exists for that. Only with the help of derivation you will be able to derive the formula. Then everyone else will get stuck in that problem and you will be able to solve it because you exactly know what is happening in the circuit, and not like, okay, I have a half wave rectifier, the average voltage will be Vm by 2 pi 1 plus cos alpha. Not like that. What does this half wave rectifier do? That is the more important part over here, right? So we will do important questions in this lecture of half wave rectifier with pure resistive load. Okay, we will try to cover all the topics with pure resistive load. So first question is calculate the, also I solved the that question that I gave you as homework, this one, right? Okay, also I derived the RMS value. So how do you derive the RMS? Simply you convert this sine square omega t into double angle formula. I hope this much you can do, right? This trigonometry you can do, and then this simply becomes a simple integration. One integration of like 1 d omega t is simply omega t, and cos 2 omega t is simply sine 2 omega t by 2 because 2 is here, so that's why, and minus sign will remain as it is, and I am going from lower limit to upper limit. Omega t equals to alpha to omega t equals to pi. You just put plug in the values and you will see you are getting the value of this integration as this. Then you will put this value in this formula for computation of RMS, and then you take the under root, you will see the same result. So that is how I derived. And about this question also I gave you as homework, this one, right? This one is same question, just here voltage and current components are a bit different. So voltage doesn't have any harmonics. So what do we need to find? We need to find the input power factor and active power. So first I will be able to compute active power, then only I will be able to compute input power factor. How to compute active power? Simply the frequencies which match. Here only 100 pi frequencies match, everything else doesn't match. The power due to all the other components will be 0. So what will be this? This will be V1 RMS into IS1 RMS or II1 RMS into cos phi 1. Phi 1 is pi by 3, that is 60. So the fundamental component is lagging by 60. Or what is a fundamental power factor or fundamental displacement fundamental displacement factor? It is basically, or displacement factor, it is basically cos pi by 3, that is half. So here I have just computed that Vs1 RMS is 100, I will divide this by root 2. Is1 RMS is 10 because I will divide this by root 2, and then I will multiply the cos phi 1. Cos phi 1 is pi by 3, so this will be half. So it will be 1000 times half is 500. Then Is RMS is what? The overall source current RMS value. So overall, so not source, this is the input, right? Overall input current value. So this will be II RMS. II RMS will be simply 10 square. Why? Because 10 by root 2 whole square, then 5 by root 2 whole square into plus 2 by root 2 whole square. So this will be 1 by 2, 1 by 2 will be equals to 11.35 amperes. Will be equals to 11.35 amperes, right? So this is my II RMS. And what is my power factor? Power factor will be simply cos phi will be equals to Py by Si. Si is what? VRMS into II RMS. So VI RMS is 100 itself. This won't change because only I have one component, and II RMS is this, right? 11.35, and at the top I have active power. Active power is how much? 500. So if I divide this will be 0.44, and this will be lag. Why this will be lag? Because here, right, if you find out the overall component, like you have to do the vector summations. If you do the vector summation of all these components, right, overall the current will lag the voltage. So that's why this will be lag. Overall angle, resultant angle will be something lagging, just like resultant RMS power current, right? So the input power factor will be 0.44 and the power drawn will be 500 watts. This is how you solve this question. Now let's come to today's question. So in today's question, this is the first question. I will go to I'm sorry if some background noise is coming. There is a bit of like people are playing TV on the left or the right of the room, that's why. So let's start this. This is the first question. Calculate if the triggering angle of the device is 60 degree. So the triggering angle of this device is 60 degree. So SCR is triggered at alpha equals to 60 or alpha equals to pi by 3. Okay. Next, peak average RMS voltage across the load. So if alpha is equal to 60, what is the peak average RMS voltage across the load? So how do you compute the peak voltage across the load? So what is VO peak? So VO peak, right? I have told you it can be two things. In the previous lecture also I have explained what it can be. It can be Vm if your alpha is between 0 to pi by 2. It can be Vm sin alpha if your alpha is between pi by 2 to pi. I've explained this. Why? Because before, if I trigger it before this, so SCR will get turned on and my voltage is increasing. Output voltage is increasing till now, till Vm, and then it will reduce. So peak voltage will be Vm. But if I trigger after pi by 2, right, what will happen? My supply voltage is less than Vm and it will keep on reducing. So when it is triggered at that moment only the voltage will be peak. So here in this case, our alpha is between 0 to pi by 2, hence it will be Vm. And what is my Vm? So they have given is 230. So our answer will be VO peak will be 230, and you will be wrong. Because you have to check that this is given in RMS. Whenever nothing is mentioned, this is given in RMS. So what do you write? You write this as 230 root, right? Because RMS, like sinusoid RMS is like peak by root 2, right? That's why this is 230 root 2. So this would be 325 point some value, 325.6 or some value. So this will be, I will write this as 325.2. So this will be used multiple times. You can like this gets into your brain when you know that 230 is the RMS, then the peak will be maximum voltage will be 335.3 volts. Okay, so this is the VO peak. Now the average. So I will write the formula here directly, but I can derive as well, right? I know how it came. So after deriving, what is does the formula come up to be? VO average is equals to Vm by 2 pi into 1 plus cos alpha. 1 plus cos alpha. So what is alpha? Alpha is pi by 3, right? So it will be Vm is what? Vm is 325.5, not 5, 325.3 divided by 2 pi into 1 plus 1 by 2, that is 3 by 2 into this. So I will just quickly compute this on my own and I will find out the answer. This will be 1.5 into 325.3 divided by 2 into pi. So this will be 77.66. Okay, 77.66 volts. This will be my VO average. Okay. Now it is recommended you remember VO RMS, but if you don't, you can also derive that as well. I derived in front of you. It will take you more time, but that's fine. But I will recommend you to remember this RMS voltage. So this RMS, right? So here this is racing load. So all formulas will be valid for this only. So VO RMS will be what? If you remember correctly, VO RMS was here, right? I had Vm over here and 2 under root pi was over here. Then this was pi minus alpha plus sine 2 alpha by 2. Now how do we make this, like how do we know that this is whatever I have wrote, right? This is correct. What you can do is you can put alpha equals to 0 here. If I put alpha equal to 0, this will be the same result as half a rectifier with diode as it switches. So if the diode is a switch, then what is the RMS? RMS is Vm by 2. So here if the alpha is 0, then this will be simply pi and this will go to 0. So this will be under root pi will get cancelled and I'll be left with Vm by 2. That's why VO RMS will be Vm by 2. So hence this is the correct formula that I wrote. Okay. So obviously you can write something wrong and that could still come out to be true, because if I write here minus, right, that could also still come out to be true. But at least you should have some check in place. If you are horribly wrong, okay, then you will be able to memorize, okay, this was the correct formula. So I will put the values over here. Vm is 325.3 divided by 2 under root pi. This will be pi minus pi by 3, right? Which alpha is 60, so this will be pi minus pi by 3 plus sine 2 pi by 3. Sine 2 pi by 3 is sine 120, right? So what is sine 120? Sine 120 is root 3 by 2. Okay, root 3 by 2, and I have a 2 over here, and that I will make it under root, right? So you have to take care that this is in radians, right? So here alpha I cannot put in degrees, you have to put this in radians, right? So with radians goes, with degrees you can put degrees. Okay, that thing you have to take care of, radians and degrees, else you will do very high amount of mistakes that you have to take care of. So this will be 3 under root divided by 2 then plus 2 into pi divided by 3. So this will be 2.57, and if I take the under root of this will be 1.59, and 1.59 into 325.3, and if I divide by 2 into pi under root, so this will be 1.45.88 volts. So this will be 1.45.88 volts. So your answer VORMS, right? VORMS. Just hold on, let me check if everything is recording or not. Yeah, everything is recording. So VORMS will be simply equals to 145.88 volts, right? VORMS will be 145.88 volts. So everything I have finished from the part A. What is the part B? Part B is the peak average and RMS current through the SCR. So what is the peak average RMS current through the SCR? So in this case, right, everything is in series. So our IS will be equals to IT, thyristor current will be equals to IO equals to load current. Everything is in series, right? And this will be simply equals to VO by R. This relation will always be satisfied. So basically I have just computed the values of VO, right? And I will just replace it here, and I will just replace the value of R. R is what? R is 10. So everything will get divided by 10. Whatever I have computed, everything will get divided by 10. So IT max will be simply, they have asked us to what? Peak RMS value through the SCR. So IT max will be simply this divided by 10, right? 325.3 divided by 10. So VO peak, because R is constant, VO is changing by 10. So this will be 32.5 some value. Okay, so it will be that 32.5. What was it? 3153. This will be my IT max, and my IT average will be what? IT average will be simply VO average by R, right? VO average by R. Now we are writing this so simply. Now I will say when all these are not applicable as well, when we will understand more load, when we will analyze more different types of load, there we will see when this relation doesn't follow. So VO average by 10. So VO average was how much? 77 point something, 77.67. So this will be 7.766 amperes. Okay. Then what is IT RMS? IT RMS will be simply VO RMS, because V equals to IR, right? It always follows VO RMS divided by R. Again I will divide by 10. So if I divide by 10, it will be 14.588 amperes. So this will be my IT RMS, right? So all these are very easily solved. Now let's go to the third part, CA part. So if I go to the C part is asking find the efficiency of the converter, supply, power factor, ripple frequency. I will do them one by one. Just hold on. So these are asking us about the, okay, where did I go? I went here, right? So this part is asking, just hold on. This part is asking about the supply side. This part was asking about the load side, and this was about the rectifier side, right? And this is also asking about the converter side. So I need to find out efficiency of the converter. If nothing is mentioned, what efficiency I will choose? How will I define efficiency? I will define efficiency like this. Efficiency will be equals to PO DC, basically how much the converter is able to give DC power from the overall power. Okay, from the overall power that is it is giving out, this is the conversion efficiency. Basically how much am I getting as DC power. So what is PO DC? PO DC I have already proven you that what is the average value. So I can write this as IO average whole square into R. That is the DC power that has been dissipated, because resistor contains what? Overall power is what? Overall power across the resistor is IO RMS whole square into R, right? This is the overall power, but this is the DC power, because the DC component is playing the power dissipated due to the DC component, that is the PODC, right? So like I want to derive a formula over here. So this IO average into R, I can write this as VO average as well. So I will keep one IO average as it is, take out one IO average, and another IO average into R, I will write this as VO average. So this is always true, right? DC power will always be IO average into VO average divided by IO average into VO average, right? And this is IO RMS into R. So this I just wanted to derive, that's it, right? Nothing else. Here, like, we can simply find it out. What we can do is we can simply cross mark this, right? If it's cross mark this, it will be IO average whole square by IO RMS whole square. Or what you can do is you can solve it like this as well. It will be VO average whole square, like there are multiple ways because V equals to IR, it is always true, divided by VO RMS. Okay, VO RMS, right? Now what you can do is, like, I will solve using this formula. Any formula you can use, right? Any formula. But am I remembering anything? No, right? I'm just deriving in front of you. I'm deriving in front of you. So efficiency is equals to IO average. I have just computed IO average. What is it? It is this, right? Not this, right? 7.76. So 7.766 ampere. 7.766 into VO average. VO average was 77.66, right? 77.66. So it will be 77.66 divided by IO RMS whole square into R. Or what you can write is, in this case, for just this case, it will be VO RMS into IO RMS, because power factor of resistance is 1. Hence the apparent power becomes the active power, right? Because load power factor is 1. Why? Because in the load I have only resistor, and what is the power factor of a resistor? It is unity. That's why. So it will be simply, I can write it as VO RMS whole square into R. What is IO RMS? Sorry, not VO, IO RMS whole square into R. What is IO RMS? IO RMS is 14.588 whole square into R. What is R? R is simply 10 in this case, right? R is 10. So if I compute this real quick, this will be divided by 10 into, or not into, 1 square into 10. In the bottom I will have 2128, and obviously I have to multiply by 100 as well to compute the percentage. So this will be 7.766 into 77.66. So this will be 603.108. okay, and this is in percentage. So if I compute this, what will be the value? So this will be 2128.3 into 100 equals to 28.337. okay, so it is actually pretty bad. It is actually pretty bad. The rectification efficiency is pretty bad, because most of the power it get is not DC. Most of the power is some other component, right? That I don't like. I only want DC, right? Most of it is ripple, because there is huge amount of ripple, and for high amount of time, what is happening? If I go back to the graphs, for high amount of time, the current is 0, right? Here voltage is 0, that means current will also be 0. And that I don't like, right? So basically we don't use this nowadays. We use something else, but just for the sake of it, I just shown you the rectification efficiency, all those things. This is very poor, right? 28% efficiency is very bad in an electrical system, right? Very bad. So that's why we won't use this, obviously. But obviously we go from small thing to higher level things, right? So to build a good thing, we have to understand the analysis of this part. Then only we will be able to understand the analysis of the complex things. So efficiency I have computed. Next, they want us to compute the supply power factor. What will be the supply power factor? Supply power factor cos phi s will be simply PS by SS. What is PS? PS is simply PO, because rectifier has no losses. So whatever input power it gets, it totally delivers it as output power, and it is SS. What is SS? It is VS RMS into IS RMS. Okay, now what is PO? PO can be written in many ways, but in this case, for my simplicity, I will write it as IORMS whole square into R divided by VS RMS, that is VM by root 2 into IS RMS. IS RMS is what? Simply IO RMS, right? Because it is a series circuit, so current will be same, so it will be IS RMS or IO RMS. Okay, so this will be simply, so this IO will get cancelled. This will be IO RMS into R. What is IO RMS? IO RMS I have just computed over here. It is 14.57. 14.57 588 into R. R is 10 divided by VM by root 2. What is VM? VM is 325, right? And VM by root 2 is RMS. RMS is 325 by root 2. That is 230. That has been specified in the question itself. So it will be 230, right? 230. And this IO has already been cancelled. So what is the answer? So if I just compute this real quick, this will be 14.588 into 10 divided by 230. So power factor comes out to be 0.634. 0.634 lakh. So basically, why will it be lakh? Because if you compute the Fourier series components, the angle of the current will be lagging with respect to the voltage. That's why this will be lakh. And if you see, this is a pretty poor power factor, right? Because I want my power factor to be as near as to 1, so that most of the apparent power that I am delivering should go out as active power that I am utilizing, not reactive power, because I can't utilize reactive power. Reactive power is being used in magnetic circuits. That is not used to us. That is not the useful power. Useful power is the active power that I can utilize. So obviously most of it I want it to utilize most of the apparent power. So it should be more near to the 1, which is not in this case, right? That's why. So next is the ripple frequency. What is the ripple frequency? Basically, how will my output voltage look like? How will my output voltage ripple? Basically, if I plot the output voltage real quick, like, it will be something like this. It is a sinusoid, but it is a modified sinusoid. This is VO. So it will be 0 in the forward blocking mode. Then at omega t, this is omega t. Omega t goes to alpha. Suddenly it will turn on. So VO will be equals to VS. Before that, current was 0, so voltage was 0. Then it will follow the supply. Then again at omega t equals to pi, again the SCR will be naturally commutated. So it will turn off. Then again this same cycle will be followed up until 2 pi plus alpha. Then again it will turn on, and so on. Right? Right? So it will go like this. So basically they are asking us about the frequency. What is the frequency? Frequency is same, right? It is repeating after every 2 pi cycles. So my ripple frequency will be equals to my supply frequency, which is 50 hertz, because they have provided the supply frequency, right? They have provided this supply frequency here. If you see, they have provided the supply frequency as 50 hertz. Next is the commutation time of SCR. What is the commutation time? Commutation time means for how much amount of time it is in the reverse blocking mode. This is the part where it is in the reverse, not this exactly, up until 0 to 2 pi, because after that it shifts to forward blocking mode. So from not 0 to 2 pi, sorry, from pi to 2 pi. So from pi to 2 pi, it is in the reverse blocking mode. So TC will be, commutation time will be pi, right? Total angle is pi. So commutation time will be pi by omega. In our case, it is pi by 2 pi f. So it is 2 pi f into 50. So it is 1 by 100. So TC is simply 10 milliseconds. TC will be simply 10 milliseconds. This will be my commutation time. Next, what are they asking? They are asking us about the average voltage across SCR. Now, what is the average voltage across SCR? Now, this is not that I have derived. So in the question, like these type of questions can come, right, in the examination, in the gate examination. Why? Because this is not I have told you to remember or formula. You have to derive, and this may so happen that you have to derive in the examination hall something like this. I haven't told you about anything about average voltage across the SCR. You have to derive, right? You have to derive. So what is the average voltage across the SCR? So what you can do is you can draw the SCR. We can draw the SCR. So if I just draw the SCR over here, and like I will go back to the plot. I will just go back to the plot here, right? I will go back to the plot here. If I can somehow copy this, that would be much. This is the voltage across this here, right? From 0 to alpha, this is in the forward blocking mode. Then it turns on. So if it turns on, it's ideal SCR. So voltage drop will be 0. Then from pi to 2 pi, again it will be negative, right? Because it is in the reverse blocking mode. So I will just copy this and I will paste this over there. So this will get cancelled. and I will reduce the size if I can. I cannot, so I will do one thing. I will just delete this. Okay, so what I can do is how to compute the average. So it is also repeating after every 2 pi, right? It is repeating after every 2 pi. So my Vt is equals to Vs for, like, I can integrate from here to here, right? Here to here, because that will be simpler. Why? I will explain. From alpha to pi, it is 0. So Vt is equals to, I'll just write this, Vt is equals to 0 from alpha, omega t equals to alpha, to omega t equals to pi. Then just after pi, right, from pi to 2 pi plus alpha, it is exactly equals to Vs. It follows Vs because current is 0, so Vt becomes Vs. That I have proved in the analysis part. So this will be equals to Vs when my alpha, when my omega t is between pi to 2 pi plus alpha. 2 pi plus alpha. Now again this is repeating, right? It is repeating after every 2 pi. So obviously now I can integrate, right? I can integrate. So what will be the Vt average? It will be divided by total time period. So which is 1 by 2 pi. Integration from alpha to pi. Not alpha to pi. Alpha to pi, this is 0, right? Alpha to pi, this is 0. So integrating it will give me 0 area. Next, integration from pi to 2 pi plus alpha. Pi to 2 pi plus alpha, and Vs, right? It is equals to Vs at that point of time, which is Vm sine omega t. Vm sine omega t d omega t. Okay, as the x-axis is omega t, that's why I choose this as d omega t. Now this will be what? This will be 1 by 2 pi. You can simply integrate. This will be minus, Vm will come outside. Vm will come outside. This will be minus cos omega t, and if I just interchange the lower and upper limits, it will be cos of pi minus cos of 2 pi plus alpha, which will be same as cos of alpha itself, right? Which will be same as cos of alpha itself. So this will be equals to what? Vm by 2 pi, Vm by 2 pi into minus 1 minus cos of alpha. So what is cos of alpha? Cos of alpha is cos of pi by 3. So cos of 60 is half, right? Cos of 60 is half. So this will be 325 divided by 2 divided by pi into 3 divided by 2, and this will be minus 77.588 volts. Now this is the method 1. This is the method 1, right? I will use a trick with which you will be able to solve the average thyristor voltage in seconds. What I will use? So what do we know is this relation will always follow, right? If I just draw the circuit, if I just take the circuit over here, just take the circuit over here. This relation will always follow. Just check this relation. That is, if I apply KVL, right, this is plus minus Vs. So if I apply a KVL in this loop, minus Vs plus Vt plus Vo equals to 0. Now even if the switch is on, close, off, I don't care, right? This relationship, this KVL will always be satisfied. So my Vt will be equals to Vs minus Vo. Now if I take the average of this whole equation, what will I get? If I take the average of this whole equation, I will get something like this. That is Vt average. This is a method 2, right? The method 2. Okay. So Vt average will be equals to Vs average minus Vo average. So what do I know is that this will be 0. Why? Because average value of a sinusoid, pure sinusoid or a pure AC signal will always be 0. So my Vt average will be equals to simply minus Vo average. So what will be this equals to? So my Vt average will be equals to Vo minus Vo average, and Vo average was what? Vo average was simply 77 point, where did it go? Here, right? Here, yeah, 77.66 volts. So this will be simply minus 77.66 volts. So this is just the computation calculation, but point wise they are bit off with each other, but this is the same thing, saying the same thing. Okay, so this is how you can solve in just 2 lines. Okay, no need to like write all integrations. So you have to understand conceptually all these things, then only you will be able to solve like this, right? Then only your brain will be able to think like this. So you have to think outside the box sometimes as well. Okay, so you can derive the formula, you can take the like method 1, or you can do method 2 where you can solve in seconds as well. Okay, this may not work always. When will this not work? Once we'll study all the load side, there I will slowly explain you in which cases this taking the overall average won't work out. I will tell you that. Okay, so let's move on to the second question. In the second question, they have told us a half wave controlled rectifier circuit is connected to a purely resistive load. Okay, the latching and holding currents of the holding currents are 10 milliampere and 5 milliampere. So like this SCR is not totally ideal because it has some non-zero latching current, that is IL, the current at which it starts to conduct, and IH, the current below which the SCR will turn off after it has been turned on, 5 milliampere. Okay, these are the definitions. So I told you, right, you have to study SCR at least before studying rectifiers. That part you have to finish. So the maximum value of load resistance that can be connected. What is the maximum value of load resistance that can be connected? Now, how do I know which condition is the maximum condition? And here they have given me alpha minimum as 10 degree. So how to use all this? So alpha minimum equals to 10 degrees. So let's assume the SCR turns on. If the SCR turns on, what is the value of the thyristor current? IT will be equals to, if SCR is on, SCR is on. If SCR is on, the value of the thyristor current will simply be this Vs upon R, because SCR doesn't have any drop. That has been already been explained. Okay, so now the next thing is that this R value, right, is variable for us. This R value is variable for us. Now here, if I keep on increasing the R, this current will keep on increasing. This current will decrease, right? If I keep on increasing the R, this current will decrease. Now for some constant Vs value, if I keep on increasing the R, this current can go below this latching current as well. And if this current goes below this latching current, my SCR will never turn on, because it is lower than the latching current. SCR can never turn on. So the maximum value that this can get, right, the maximum value R max will be what? If I place the R that side, this will be Vs divided by I min. Okay, Vs divided by I min. That is the maximum amount of current that this can provide it, right? That is the maximum amount of there is a minimum amount of current due to which the SCR can turn on. And one thing you have to notice is that this alpha minimum, right, is 10 degrees. So if I just trigger it at 10 degrees, it should turn on at 10 degrees. So my voltage Vs, whenever I want to trigger it should turn on, right? Whenever I have triggered at omega t equals to alpha, it should turn on. So at omega t equals to alpha, what is my Vs? Vs is, this is again RMS value, right? This is again RMS. So it will be 200 root 2 sine of alpha. So generally sine wave is given. So this will be sine of 10 degrees. So Vs value is this. And at this voltage, due to this voltage, whatever current that flows, right? Whatever current that flows, that should be equal to my latching current. Then only my SCR will be turned on. Hence, my R max will be this. What is this value? 200 into root 2 into sine. So this is 49.11 divided by IT. IT minimum was minimum current needs to be latching current, else it won't turn on. So what is the latching current? Latching current is 10 milliamperes. To 10 milliamp, that will become kilo basically. So this will be 4.9115 kilo ohms. This is the maximum value of resistance that I can put, above which the current will reduce below the latching current and it will never turn on. Okay. So next is the maximum conduction angle of the thyristor if the value of the resistance obtained from the previous part is used. So the resistance value is this, and they are asking what is the maximum angle at which it will conduct. So the SCR has turned on. Then when will the SCR turn off? The SCR can turn off. SCR, just hold on. SCR can be off. SCR can be off. When will SCR be off? SCR will be off when either it is in reverse blocking mode or it is in forward bias mode. It is on, or it is on and current IT is less than or equals to holding current. If the current reaches lower than holding current, then it will turn off. These two conditions can happen. So when this happens when my omega t equals to pi, the like it becomes reverse bias, reverse blocking mode, and this will happen when. So what is the expression for current? What is the expression for current IT? IT is simply Vs by R, right? Because when the SCR is on, this is the expression of current. So this is equals to Vm sine omega t divided by R. R we have already computed. So when this at for some particular time omega t, this becomes equals to holding current, then this can turn off, right? And what will happen? Let me just equate this. So like there is one term known as beta, that is known as the extension angle, that angle at which the device turns off. That we will learn later on, don't worry. So I will name this as beta. At beta, my current IT is less than or equals to IH, holding current. So what is the holding current? Holding current was 5 milli, right? 5 milli. And what is R? R is equals to 4.9115 kilo, right? Equals to Vm is what? Vm is definitely equals to 200 root 2, and this is my sine omega t. Now if I just compute this real quick, this will be divided by 10 into 5 divided by 200 into root 2. Okay, and then do the sine inverse. So like your angle is coming out to be, omega t is coming out to be, or your beta at omega t equals to beta. Beta is coming out to be 4.98. Now is 4.98 possible? 4.98 is not possible. Why? Because you are only triggering at 10 degrees. So obviously it will be 0 at that point of time, and that is not possible. But we know one formula, right? Sine pi minus theta and sine theta are same thing. So here if I write this as 180 minus 4.98. So this will be almost equals to just hold on, if I am doing some mistake over here. Yeah, what are this? The maximum conduction angle of the thyristor is the maximum conduction angle. Yeah, actually there is a bit wrong here. The maximum conduction angle is fine. The third question should be the conduction period of thyristor. Actually, like there is a bit of confusion in the terminology. That's why I am changing this question a bit. So basically, right, what will happen here? I will just do this thing, then I will explain. And this is the maximum angle is conducting. So why, I will explain just in a bit. Let me just reduce the size of this. Okay, so here, right, I was solving it, the maximum angle at which the SCR is still conducting. So the SCR here is conducting still at 170, almost equals to 175 degrees. So but we know for an ideal SCR, right, what would have happened? It would have conducted till 180 degrees. But for a non-ideal SCR with a finite like non-zero holding current, what will happen here is that as soon as the current reaches below the holding current, the device will automatically turn off. Even if the voltage is positive, it will go to forward blocking mode. Okay, even if the voltage is positive but the current has reduced, so it will go into forward blocking mode. So this is my answer. Okay, and what third part, what are they asking? They are asking us the conduction angle or the conduction period, right? The period for which the SCR is conducting. What is the period for which SCR is conducting? The SCR starts to conduct from alpha and it ends at beta, right? Ends at beta, because after that current becomes 0. So it will be simply conduction period. This is also defined as gamma. This also I will explain. These terms I will explain later on, don't worry. Okay, this will be beta minus alpha. So this will be simply 175 minus 10 degrees. So this will be 165 degrees. If they have asked in radians, so you can convert this into radians by doing what? By multiplying by pi by 180. Okay, 165 degrees into pi by 180. So basically what happens is this degree unit gets cancelled out and only this radian unit is present. That's how I remember this formula to convert from degree to radian. Okay, let's go to the next question. So in the next question, right, what are they asking? For the below circuit, the maximum voltage blocked by the ACR is 120 volts and the trigger angle is 70 degrees. Then power consumed by the load. Okay, so for this to understand, right, what do we mean by maximum voltage blocked by the ACR? So here, right, maximum voltage blocked by the ACR, maximum voltage blocked by SCR basically means it is talking about the forward blocking mode, because in the reverse blocking mode anyways it blocks the voltages, right? And whenever they will talk about reverse, they will talk about that, they will say it is the peak inverse voltage, because during reverse blocking mode the maximum voltage is the peak inverse voltage. It is defined as the peak inverse voltage, right? That I have defined the definition, the voltage when ACR is reverse bias or when the diode is reverse bias. So this is talking about the forward blocking mode. So in the forward blocking mode, how does the waveform look like? So in the forward blocking mode, just hold on a second, let me just check if everything is fine or not. Yeah, everything is fine. Everything is recording. Yeah, so in the forward blocking mode, right, in the forward blocking mode, SCR, the maximum voltage that it blocks is Vm sin alpha if our alpha is between 0 to pi by 2. If our alpha is more than pi by 2, then obviously it has to block this much amount of voltage as well, that is Vm, right? Vm. Okay, so maximum voltage blocked by the SCR, Vt max, can be two things. It can be Vm, if my alpha is between pi by 2 to pi, but it will be equals to Vm sin alpha, the value of the supply voltage at that point of time, if my alpha is between pi by 2 to 0. Why? Because after that what will happen? SCR will turn on, and as soon as the SCR turns on, the voltage becomes 0, and this much amount of voltage only it has to block, right? So the maximum voltage will be Vm. Now what have they given? They have given us the alpha 70, which is less than 70. Sorry, they have given us the alpha 70, which is lower than 90 degrees. So obviously we will take this case. So information that has been provided to us is that Vm sin alpha will be equals to 120 volts, right? 120 volts is the maximum voltage that it is blocking. So sin alpha will be what? I'll just check. Sin alpha will be alpha is 70. So 70 sin, and I have to divide this into 120. So our Vm, right? Our Vm will be what? Our Vm would be simply 127.7 volts. This is the value of our Vm voltage. This is the value of our Vm voltage. Okay, so we got Vm, but why do you need Vm? Because for that we need to find the power consumed by the load. And what is the formula of power consumed by the load? The power consumed by the load you can find out either with IORMS whole square into R, or VORMS whole square into R. Only this is valid only when our load is purely resistive. So here what is VORMS? We know, right, what is the formula for it. You can derive it always, but it goes to remember. So it is V by 2 under root pi. I am just writing the VORMS for now, so this I will put this in bracket, and 1 by R will be present here, and this is pi minus alpha plus sine 2 alpha by 2 whole under root, and if I square it, okay, if I square it, this will simply whole under root will be cancelled, okay, and this will be square, and this will be also square, right? Now what is R? R is 10, right? R is 10. Vm I have just computed, it is 127.7 whole square. This will become 4 by pi, and this is what is alpha? Alpha is 70, right? So alpha is 70. If I just compute this 70, I have to convert this 70 into radians, right? 70 into pi divided by 180, then plus sine 2 alpha, that is alpha is, so sine 40 upon 2 plus, so this will be almost 1.5 5431, right? So if I just compute this real quick, divide by 4 into pi, okay, into 127.7 whole square divided by 10. So this will almost come out to be 200.2 watts. Almost come out to be 200. Yeah, sorry for the interruption. I just made a calculation mistake over here. This won't be that one, whatever value was coming. This should be 2.241. That's why I was confused. And if I just find out the power, right, my power will be simply 290 watts. Okay, this will be the answer to this question. Let's move on to the next question. So the next question: a single phase half wave rectifier is delivering power to a pure resistive load. Fine. Calculate load power if the turn on resistance of the diode is 1 ohm and power dissipated by the diode in the conduction period is 10 watts. Okay, so the turn on resistance is 1 ohm and it is also dissipating 10 watts of power. Then what is the power delivered to the SCR? So how do you solve this type of question? So there are two methods to solve this question, right? One is like through waveforms, another one is simply objective way. So what is the objective method? So whenever the diode turns on, right, whenever the diode turns on, okay, so if I just draw the circuit, if the diode turns on, the circuit will be something like this, because this will turn on alpha equals to 0, right? There is no triggering angle because this is not ACR, this is a diode. So whenever the input voltage is positive, this diode will be turned on. This is my R and this is my small turn on resistance, and this is my supply R on. Okay, so what is happening here is that what is the power consumed in the resistance? The power consumed in the resistance will be simply IRMS whole square into R. This is the power consumed in the resistor. That is what they are asking. What is like the IRMS? If I'm able to find the IRMS, I will be very happy. How will you find? So you can use your objective brain that during the conduction period the power dissipated is 10 watts, and only this current will flow, else current will be 0. So they have given me this information that IRMS whole square into R on, right, the power dissipated in the diode during conduction period is 10 watt, and I know R on is 1 ohms, and I know this 10 watt power, so I will be able to compute my I square RMS, okay, very easily. That is under root of 10, so it is almost equals to, I believe, 3.16. yeah, IRMS or I square RMS will be 10, so IRMS will be 3.1623, okay, 3.1623. So my power will be what? Power dissipated across the resistor will be what? Simply IRMS whole square, that is 10 into R. Now how do I find out this R, right? How do I find out this RL? This is RL. How do I find out this RL? So finding out this RL is very interesting, because one information I know IRMS, right? I know IRMS. From there, can I conclude anything? So basically, what you can say is your IRMS will be simply equals to this VO RMS by R, right? This relation will always follow. Now what is this VO RMS? How do I compute this VO RMS? So this VO RMS is simply equals to, like, if you observe, what is this VO? VO is simply equals to VS into R on, not R on, sorry, into RL divided by RL plus 1, RL plus R on, right? So what will be the RMS value of this? So this is for 0 to omega t equals to pi, because after that VO is simply 0, right? After that VO is 0 because diode is turning off, so it will be 0 after that, okay, from pi to 2 pi. So what is the RMS value for this? This is also simply a sinusoid, just an external factor is here, right? Just an external factor is here. So how do I compute the RMS value of this? So it will be same, like this is just a sinusoid, right? And this factor is just getting multiplied. So what will be my IORMS? So basically, if I want to compute this, right, VORMS, if I want to compute VORMS will be simply integration from 0 to 2 pi, but as in this case from pi to 2 pi the value of VO is 0. I will just integrate from 0 to 2 pi, 1 by 2 pi. This will be VS into RL by R on plus RL, this whole square, d omega t, and I have a under root as well. Okay, this is my RMS. Now this is a constant, right? This is a constant, this I can take outside. So this will be RL by R1 plus RL whole square, and if I take outside this under root, this will be simply just a mere factor, that is RL divided by R1 plus RL. You learn more about this. This is just like we are dividing it by some factor. The area is getting reduced. This we will learn more about in signals and systems. Okay, so this will be 1 by 2 pi, 0 to pi. Vs is Vm sine omega t whole square. Okay, sine square whole square d omega t one by 2. Okay, 1 by 2. Hence, what is this? This we have just derived, right? This is for alpha equals to 0, uncontrolled rectifier. For alpha equals to some value that we know what is VORMS. VORMS is this, right? For alpha equals to some finite value, for non-zero value. If I put alpha equal to 0, this will be simply Vm by 2. This will be simply Vm by 2, right? So this will be what? This will be Vm by 2. This will be Vm by 2 into RL divided by R1 plus RL, have a 2 as well, right? Have a 2 as well. So this is VO RMS. Okay, this is VO RMS. So this is my value of VO RMS, right? And what is VO RMS? VO RMS is simply VO RMS by R. So what is IO RMS? VO RMS by RL, right? That is my IO RMS. So from here I will be able to simply find my value. So what I will do is yeah. So what is VO RMS? VO RMS I can write this as IO RMS into RL equals to this value. I will just copy and paste this, Vm by 2. So many educators, what they do is they directly write this, they don't derive, but still I derived, right? Or all these things I did. Okay, so this will get cancelled, and IO RMS I already know, that is 3.1627163 or whatever. Okay, RL will get cancelled, and this will be 2 into 1 plus RL, right? 2 into 1 plus RL, and Vm is what? Vm, they have given us the supply as 230. This will be maximum will be 230 root 2, that is we write this as 230 root 2. Okay, this will be 325. So I will just compute the RL value of RL real quick. So times 2 into 230 into root 2 and subtracted by 1. So RL will be 50.429 ohms. So this is a very good question, right? Because RL, finding the value of RL was the trick of this question. Okay, so now you have found out RL. So what is my power lost across, or power dissipated across the resistor? It is simply IO RMS whole square into RL. Although this also took some time, obviously these things will take time, right? So this is 10 times this 10 times that. IO RMS whole square is 10, so it will be 504.3 watts. Okay, almost this will be your answer to this question. Okay, so this is a very good question. Now what is the method 2? Method 2 is simply with the graph. So you find out with the graph, right? So this is your Vs supply, and this is what? This is the diode voltage, right? This is the diode voltage. So what do? You find out the RMS across this diode, okay, across this diode, RMS value of this diode, and from this RMS you find out how much power this is dissipated. So this area will be equals to 10, and you will find out from this value you will be able to find out the value of RL, okay. And after finding out RL, you can simply find the area under this, and you can put the unknowns here, and you will be able to simply find, okay. So basically this is the RMS from graph. This is the method 1, right? You find method 2, you find the RMS values from the graph, and you from here you find the value of RL, okay, because the conduction loss has been given. So RL you will get as 50 value, 50.429, and you plug in this here, okay, and you will be able to find out your power loss in the resistor. So this is a very good question. This method will be a bit slow because you have to find out the area and integration of all those things, and square also. That will be very difficult. So what is the interesting fact over this is, like the IORMS for this, right? IORMS for this, so will be simply what? So one thing I have done a bit, okay, this is the voltage divisor, and IORMS for this will be what? IORMS will be simply this voltage will only be present, so it will be Vm by 2. So what you can do is, just I will draw the graph of IORMS, there you will understand. So what do I mean by this? So this is the graph of what? This is the graph of VO, and VO and IO are directly proportional to each other, so that isn't a problem. But what about ID? If I draw the graph of ID, right? If I draw the graph of ID, what will be the graph of ID? So omega t. So graph of ID will look something like this. Okay. This will be 0. Then again it will go on. So from 0 to pi, what is this peak value? This is also a sinusoid, but this is a attenuated sinusoid. The peak value will be this peak divided by the resistance of the diode, that is RD on. So this will be Vm by R plus, not R, RL plus R. Now can you find out this is what? This is I M. So from here what you will be able to find is, like the RMS, IORMS will be simply equals to Im by 2, right? This is the value of the RMS for a half rectified sinusoid, okay, that you have found out, okay. And if you put here value as whatever, like you got this IORMS, right? You equate this, then you will be able to find RL. And what is ID? What is IO? IO is simply this, right? And you have found out what is IORMS, you know what is IORMS, and you have found out RL, and from there you can simply derive. So this is also a good method. Right? So you have to understand graphically, you have to understand conceptually as well, and theoretically as well, like with objective method, okay. So let's now go to the last question. This will be the last question of this lecture. A single phase phase controlled rectifier provides maximum output voltage of 250 volts across the resistive load, and the maximum voltage blocked by the SCR in reverse mode. So they have specifically said in reverse mode. So question will be more better if they specifically mention in which mode they are talking about. If they haven't mentioned anything and they are not talking about peak inverse voltage, so most probably they are talking about the forward blocking mode, okay. So in reverse mode it is blocking 480 volts, then the firing angle of the SCR in degrees. So in reverse mode the maximum voltage, peak inverse voltage, it is 480 volts, and we know the SCR always block reverse voltage, so the maximum voltage, peak inverse voltage will be this equals to Vm only, right? And at the output, the maximum output voltage is 250. So I am observing that the maximum VO max, right, is less than the input maximum, voltage, okay. Now what does this mean? This means basically my alpha lies between pi by 2 to pi. This, why is this the case? I have told this graphically. I will not explain it here again, right? I will not explain it here. So alpha will be greater than 90 degrees. So basically my Vm is 480, hence I can write my Vs as what? 480 sine omega t. And if my alpha is lying in this range, right, then what will be the VO max? VO max will be simply Vm sine alpha. It will not be Vm, right? Because the voltage is reducing ever since. So VO max they have given me as 250 volts. So 250 will be equals to 480 sine alpha. So sine alpha will be simply equals to, if I just compute this value, 250 divided by 480. Do the sine inverse. So this alpha, okay, alpha comes out to be, just hold on. Alpha comes out to be 31.38 degrees. Now will I take this? No, right? I will not accept this because I've already assumed my range of alpha. My range of alpha is this. This is not possible because if my triggering angle is this, right? After this, what is happening? My sinusoid voltage is something like this. If I trigger it somewhere around here, the voltage will still increase and the maximum voltage across the output will be Vm, not less than Vm, right? But I can write this as this, right? 180 minus theta as well. Sine theta is 180 minus theta as well. So if I trigger at this point, the voltage only reduces. It doesn't reach to this Vm, right? Voltage only reduces. So this will be the peak value. So obviously my alpha will be 180 minus this 31.38 degrees. So plus 180. If I do it, so this will be 148.62 degrees almost. Okay, so this will be your trigger angle. Okay, this won't be your trigger angle because after this the voltage is increasing still and maximum voltage appearing across the output will be Vm. Okay, so these were a few questions for this lecture. I hope you like this lecture, and in the next lecture we'll start with more half-wave rectifiers with different loads, right? With RL, RLE, and after that we'll learn about freewheeling diode and filters. So yeah, thank you for watching and I will see you in the next lecture.